Hello friends, so in this tutorial we'll be learning how to run object detection using Pytorch. So the algorithm we'll be using is the SSD algorithm, which stands for single shot detection. So before we get started, if you are new here, kindly subscribe. Alright guys, so start off by looking at the file systems as usual. We have some images here which we'll be running inference on. We have about 4 or 5 images, and the images including the code will be on my GitHub repository, so you guys can leverage it and use it. Also, we'll be using this class because whatever we are going to do is based on the Cocoa dataset. So we'll also reading this class so that we'll get the label for any object detected. Okay, so since we are done with the file system, we'll go ahead by importing the libraries we will need. But before that, I'll go ahead and create a new Python file which I'll call Pytorch SSD. After this, I assume you've installed Pytorch and all other libraries we'll use. So I'll also put requirement.txt file which you can install the libraries necessary for this particular tutorial. So we start off by importing Torch and also import Torch Vision, which will help us to load our SSD model. So we also import transforms from Torch Vision so that we can be able to transform our image into a Pytorch tensor. So we import, that should be from Torch Vision, we are importing transforms, and let's import it as T. To read in some images, we have to import OPCV, and I think that's it. If we need other libraries, we'll come back and just import them. So the first thing to do here is to load in this pre-trained model. So we'll specify our model, which is equal to torchvision.models.detection and then the SSD model. So this is the particular model we'll be loading, SSD 300 VGG16. And since we are going to use the pre-trained model, we have to specify here that pre-train is equal to true. Then after this, we can check the model architecture by just writing model.evaluate or model.eval, and what we'll do here is to print it. So we'll go ahead and just print the model architecture. So I'll put this one here, and then I will just run the file so that we can see the architecture of the model. There are some warnings here, but you have to ignore them. So guys, this is the architecture of the SSD model. You can see it's very long. We have some convolutional neural network, ReLU activation function, and ton of these stacks together. So you can see it's a very big model. So we just close this off and continue with whatever we want to do. We don't want to print the architecture again, so what we'll do is just put the model.eval, which is necessary because if you don't put it, you can't use the pre-trained model. You have to evaluate it. Then after this being done, now we have to read in some image which will perform the detection on. So as I've shown you earlier, we have many images here, so I'll just use the OPCV library to read one in using the imread function. Now I'll just read man.jpg as an image, and we can go ahead and print the type of this image. So let's run this up, and you can see the type of this image is numpy, so ND array. And the thing is, in order to do predictions on Pytorch image, you have to convert this image to Pytorch tensors. So what we'll do is that we will use the transform to create a transform object, and then we'll pass in our image, and this image will be converted to a Pytorch tensor. So I will call this img transform, or img trans here, that should be transform, is equal to t dot to tensor. So we are using the transform we've imported here. Then we just put it like this, and then we can just pass this image into our transform object by just writing our image, which is equal to image transform, and then we just pass in our image. So we are just passing this image to our transform object here so that it will convert it to a tensor, and we can verify that by printing the type of our image once again here. So at first we are printing it, which we know is a numpy array. Then secondly, we will print it here also to check whether it's successfully being converted to a touch tensor. So you can see first we are having it as a numpy array. Then after performing the transformation, is now in a touch tensor. So this is working great. So we'll go ahead now and pass this image to our model, and we'll get predictions from it. So we can write ypred, which is the prediction we'll get, is equal to our model. Then we have to pass this image as a list, so we just write our image here, and we'll print it and get our prediction. So we just print ypred. Let me quickly close this off and increase the font a little bit. So let's run this. You can see we have ton of predictions here, so let's take it one by one. I think it's a list. So this is a Python list, and it contains a dictionary in this case. So we have boxes. So these are the coordinates for all the boxes detected on the image. So we have 4 of them, of which this is the x, the y, the width, and the height of the image detected. So a lot of boxes are being detected. Then also we have another key here, which is the scores, how confident is detecting. Then lastly we have our labels. But what is happening here is that we are still tracking our computational graph, which is graph fn, or backwards. So we have to get rid of it because we don't need the computational graph. And to do that, we just have to say with touch dot no grad. We don't want to track the computational graph, so we get rid of it, and still we can run this and it will still work. So you can see we are not having the computational graph kind of thing. We just have our predictions, and that's it. So since this is in a dictionary, we can try to get the keys from it. So we can say we are printing the ypred at index 0, then we go dot keys, and this is a Pythonic thing, so running it, we can just get the keys of this particular prediction. So you can see we have the keys, of which we have the bounding box, we have the scores, and we have the labels of whatever we've detected. So we can go ahead and extract this one by one, then we can choose to print, or we can choose to use which one we want. So since it's a dictionary, we can go ahead here and say, okay, our bounding box, our scores is in this order, and lastly our labels is equal to, so I can copy this and paste it here, ypred at index 0 in the key of boxes. So first you are taking the bounding box, then we can do the same thing for the rest of them, which is the scores and the labels here. So we will paste this a couple of times, and then instead of boxes we change here to scores. Then this will be our labels. If I score label correctly. Okay, so Now we can get access to each of them individually. For instance, we can just print only our box, and we can run this app to check whether we are getting only the bounding box information. So you can see, instead of getting everything, we are only getting the bounding box information. We can do same for our labels and our scores as well. So let's check for the scores, and boom, we are getting it for the scores. So it's detecting something with an accuracy of 93%. So what we'll go ahead and do now is that because we have many scores, many bounding boxes detected, we have to make our prediction based on the confidence. So to do that, we can iterate through all of the boxes or some of the boxes that have higher accuracy, and then we'll take that boxes as the objects detected. So we can say nums is equal to our touch dot arg, where our score is greater than, so let me separate this, is greater than 0.60. let's do it like that. So we can come and print nums here, then we see what we are doing. So you can see we have a tensor, we have 0 and 1. That means we have two bounding boxes or scores that have a higher accuracy than 60%. So those are the boxes we are going to use. So we can even make it 80%. That means we are saying if we detect anything that has an accuracy of 80%, we want to extract the bounding box and then the label of that particular thing, then we draw it on it, so that we don't just draw all those bounding boxes detected with low confidence or low scores. So in order to get this in a number form, we can just take the shape of it at in the 0, which is the first one. So now if we print nums here, it will be a single number and not an array. So we have 2. That means we have two bounding boxes that have an accuracy more than 80%. Let's try 90 and see. And with 90, we have only one bounding box that have the confidence more than 90% and above. So let's keep this at 80, and then we can iterate through all the boxes and then take the boxes that have that accuracy, then we draw it on our image. So we can say for I in our nums, or let's do it, therefore I in the range of our nums, we want to get our x coordinate, y coordinate, our width and the height of whatever is detected, and this is equal to our bounding box of I. Then we have to convert it back to numpy. If you remember, our image is in tensor now because we have done transformation over here, which we convert it from numpy to Pytorch tensor. So we have to convert it back to numpy so that we can draw on it using the OPCV library. So we say .numpy. And also we shouldn't forget to also change the type to an integer, because we have floating numbers there as the bounding box. So we can just say as type, then we specify it to be an integer value. So with this out of the way, we can go ahead and draw this rectangle on the image. So we can say cv2.rectangle, then we want to put it on the image. But this image now is also a Pytorch tensor. So what I will do is to come to the top here and then copy this image. Where is it? This same image. So we'll say img is equal to our original image dot copy, and that's all. So we are copying this image, we are getting a copy of this image and want to draw on it. So we draw on this image. We have to specify our first starting point. So starting point of this rectangle should be x and y. Then the ending point should be the width and the height. After that, you didn't forget to specify the color of the rectangle. So let's make this red, 0, 0, and 255 to make it red. Then finally, we can make the thickness of this rectangle to be 5. So after this, we can go ahead and show these bounding balls on our image, but it shouldn't be in a loop. So cv2.im show, give it a frame name, and what we want to show here is our image. To keep this image on the screen, cv2.wait key, which will help us keep the image on the screen. So wait key of 0 will keep this on the screen. So let's run this app. And boom, you can see we have the human being detected, and the dog is also being detected. But now we don't have much information about whatever is being detected, though we have bounding balls, but we don't know whether it's a person or not. So go ahead and use our classes.txt file, which is based on the Cocoa dataset, to check for that, to see whatever is being detected in real life. So we'll close this up, and I can open here now and then open the classes.txt, which contains all the common objects you can detect. So this model can detect all the 80 or 82 classes here. So these are objects you can detect, and these are the objects which are mostly with us. So you can detect anything here using this particular model we are using. So now let's read in these classes into our Python file. Then based on the label, we can choose whatever is being detected. So we'll come here right after loading the model, and then we'll say our class names. Class names is an empty list, and then with open, this is just reading file in Python. We want to read our classes.txt file, and we want this to be in the read mode because we are reading from the file, and then we are reading it as F. You can choose any alphabets. Then class names is equal to f.read. Then that's all. You can also put them on each lines by using the split lines method. So after this, we will get everything. We'll read everything from this class here into our Python code, and to testify that or to check whether that is working, we can print the class names at the first index, which is 0, and we expect this to be a person. So let's run it. Let me raise this up, and you can see we have person as the first thing detected. That means we are reading this accurately. Okay, so we can comment this up, and what we'll do here is to get our labels. So we'll say our class name is equal to our labels of I, and don't forget you have to also convert this to numpy. So .numpy, and then the type to an integer, .astype int. So this class name here is only going to be a number, and whatever number we are getting here, will match it to its corresponding class name here. So that's what we are going to do. And what we'll do is that we can print this class name to see which numbers are being detected. And you can see we have detected number 1 and 18 because we have detected 2 objects. And if we open the classes.txt file, you can see number 1 corresponds to person, and number 18 here corresponds to dog. So That means the model is accurately detecting whatever is in that particular image. So now let's map it. Instead of getting these numbers, we'll get the actual name of whatever we've detected. So we can give this class detect as detected is equal to our class names which we have read in the key of class name. Then we have to subtract 1 from it, because in Python indexing starts from 0, but with our file it starts from 1. So I'll close this up, and now instead of printing class class name, we can print class detected. And let's run this once again. So you can see we have person and a dog. So a person and a dog is detected in the image, which is correct. So the final thing we will do now is to put this on the image. So if it's a person, we have a person on the image. If it's a dog, we have a dog on the image. So we can use OPCV to put text on an image, but we can also use another package called the CV zone. So import CV zone, which will give us a nice text. So let's import CV zone. What we'll do is that we can comment this up, and then we'll say CV zone dot put text rect. I want to put this text on our image, and then the text we want to put is the class detected, and then you have to specify the position. So for the position, you want to put it at X, and then we can say Y plus 100. So this position you can change. You want to put it from the beginning of whatever is being detected, then in the Y plus 100 position. That means you come towards the middle part of it. Then we have other stuff you can specify, such as the scale of this text. The border is also there, so let's put it 2, and this is it. So let's run it and see how it displays now. So wow, this is nice. You can see we have a person detected, we have a dog also detected with their name on it. So this is how easy it is to just detect things using the SSD model. And for the moment of truth, we can also use other images we have here, such as the cat image, and then we'll run this and see whatever will be detected in these images as well. And boom, you can see cat is being detected. So you guys can try this with all the classes we have here and see how it works for you. Anything outside these classes will not be detected. So that's the baseline here. What other image will I try? We have here man, dog, we have dog, Oli. So let's run this for the last time, and you can see we have this weird dog being detected as well. So guys, this is working accurately. This model is working well, and this is where we'll bring this tutorial to an end. So if you like it, as usual, kindly like, share, and also subscribe if you are new. Thanks for watching, and I'll see you in the next tutorial.